After Röntgen discovered X-rays in 1895, scientists speculated they were very short electromagnetic waves, but couldn't prove it due to the lack of a suitable diffraction grating. In 1912, Max von Laue proposed sending X-rays through crystals, using their atomic structure as a natural diffraction grating. His colleagues, Walter Friedrich and Paul Knipping, confirmed this by irradiating a copper sulfate crystal, producing a pattern on a photographic plate. This discovery, praised by Einstein, earned Laue the 1914 Nobel Prize in Physics. Max Laue, born on October 9, 1879, in Pfaffendorf near Koblenz, grew up in several German cities due to his father Julius von Laue's military career. His education in Berlin, Posen, and Strasbourg shaped his early interests, with Professor Goering at Strasbourg's Protestant school sparking his passion for the exact sciences. Max Laue began his studies in mathematics, physics, and chemistry in 1898, eventually earning his doctorate under Max Planck at the University of Berlin in 1903. His career included key roles at Munich, Zurich, and Frankfurt, where he lectured on optics, thermodynamics, and relativity. During World War I, he focused on developing high-vacuum tubes for telecommunication systems. From 1919 to 1943, he served as professor of physics at Berlin while consulting for the Physikalische Technische Reichsanstalt, leaving a lasting mark on theoretical physics. In 1917, Max von Laue became second director of the Institute for Physics in Berlin-Dahlem, working alongside Einstein. During World War II, he moved with the institute to Hechingen and wrote a history of physics, which was widely translated. After the war, he was briefly held in England, where he contributed a key paper on X-ray diffraction. In 1946, he became acting director of the Max Planck Institute in Göttingen and later led the Fritz Haber Institute in Berlin. In the early 1900s, Munich's Hofgarten Café became a vibrant meeting place for physicists, artists, and thinkers, where groundbreaking discussions shaped the future of science. Arnold Sommerfeld's daily coffee sessions with scholars like Abraham Joffe and Max von Laue led to profound discoveries. One evening in February 1912, Peter Paul Ewald sought von Laue's advice about difficulties in his doctoral thesis on the behavior of long electromagnetic waves in hypothetical crystal lattices. While von Laue couldn't directly answer Ewald's question, he speculated that X-rays could be diffracted by the atomic spaces in crystals if their wavelengths matched the lattice structure. Encouraged by Sommerfeld, von Laue designed an experiment with a copper sulfate crystal placed between an X-ray tube and a photographic plate. Von Laue's groundbreaking discovery of X-ray diffraction was achieved through a meticulous experimental approach. The key materials included an X-ray source, typically an X-ray tube, a copper sulfate crystal known for its regular space lattice structure, and a photographic plate to capture the diffraction patterns. The experimental procedure began with positioning the crystal in the path of the X-ray beam. The crystal was then irradiated along specific crystallographic directions, allowing X-rays to interact with its atomic lattice. The resulting diffraction patterns were recorded on the photographic plate, where bright spots emerged as evidence of X-ray interference. These interference points were analyzed, with their positions and intensities corresponding to the periodicities of the crystal's space lattice. This process not only demonstrated the wave-like nature of X-rays but also enabled the calculation of their wavelengths, affirming the crystal's role as a three-dimensional diffraction grating. The experiment confirmed the wave-like nature of X-rays and their ability to interact with the atomic lattice of crystals, resolving debates about their nature and validating atomic arrangements. This discovery earned Max von Laue the Nobel Prize and established a foundation for advancements in crystallography. Max von Laue's discovery of X-ray diffraction in crystals was a transformative milestone in physics, confirming the wave nature of X-rays and revealing the lattice structure of crystals. His meticulous experimental approach and mathematical modeling resolved long-standing debates and laid the foundation for advancements in crystallography. Recognized with a 1914 Nobel Prize in Physics, his contributions continue to inspire scientists exploring the atomic and molecular structures of matter. Von Laue's work not only bridged theoretical and experimental physics but also ushered in a new era of understanding in the scientific world.